All right. Who has a midterm tomorrow? A lot of you. Right. So to that end, I just want to point out, in case you missed it, I did post another practice midterm that is very similar to the one he wrote. You can find it in Canvas if you look in the modules. If you scroll down a little bit further to the exam prep material. Here's the one I wrote. Is that the one I wrote? Yeah. So there's the one I wrote. There's the solutions. There's the video of me going through the solutions. And then there's Babson's practice midterm and also solutions I wrote to it. They're the same as his, but written by hand instead of like text. So if you're looking for more resources, that's where I would suggest going. To that end, we can certainly go over some or all of it. But before we do that, there's two things I want to talk about briefly because we haven't talked about them yet, and they were on the practice midterm. So let's start with that. Also, there's stuff we're going to cover anyway. So the first thing I want to talk about is more U substitution with back substitution. So here's an, oh yeah, question. Sure. I I know nothing about the cheat sheet. So I don't know. So let's go take a look. So if we look over here at Babson's website, where are you, Babson? You're over here. You're somewhere in here. There you are. You're hiding. And if we look at his web, I should just bookmark his website because really I just go here and the thing. You just scroll down. I know. Let's actually take a look at the practice midterm because I feel like on the practice midterm there was. Let's see. You may use one page of notes, but not a calculator or a textbook. Please do not simplify. Oh, that's good to know. Please do not simplify your answers. So it's good to read those instructions, right? Because you don't want to waste time simplifying an answer for two reasons. One, it's a waste of time. Two, you might make a mistake doing it and lose points because you spent time doing something you weren't asked to do in the first place. So what was your question specifically? So yes to front and back. Do we know if you can print it out or does it has to be handwritten? If I had to guess, I would guess handwritten. That's what I would assume you should ask though. Like, so if nobody knows the for sure definite answer, you should ask. But also, handwritten is definitely what people want you to do, even if they don't say that. So that's certainly the intent is for you to handwrite them. Obviously, that might give somewhat more advantage to people that are able to write more neatly or smaller, but that is life. But don't try to cheat the system. Don't like write it up by hand and then like print it smaller. Like someone might see something if that's what you're not supposed to do. And so just also really the reason they say to write it out is so that you learn the things you're writing down as they're like, oh yeah, I know those formulas. Yeah. Oh yeah, at the bottom of the website. Let's see. Let's we go back. Under exams. Sure.
Says, oh yeah, exams, one sheet of notes, both sides is allowed. And that's all he says.
Okay. So again, I would default to handwritten because that's usually the spirit of the notes, but you can also try to get away with whatever you can get away with. So you do you. But that's what I would do. I would write them up by hand. All right. So back to the couple topics I want just to, it's actually the same topic really. So some integrals with U sub and back substitution. Here is an example. Something like x to the fourth times 2 plus x to the seventh to the 23rd power. So we obviously can't multiply. I mean, one could, but we're not going to multiply out 2 plus x to the seventh to the 23rd power. It's a lot of terms. So there's a U sub probably hiding somewhere. And it seems like the plausible choice for you is the thing inside the parentheses. So we're going to start with just saying, well, we're going to let U equal 2 plus x to the seventh. And we really, really wish the derivative of that was in our integral, but it's not. Oh, did I want, sorry, now I have to make sure I'm doing the right thing. One moment, please. That should be right. So I have to make sure I'm not screwing it up. I am screwing it up. So this one is totally wrong. Bless you. Sorry. This is what happened. One moment, please. That's not going to work out well at all. I meant for it to be this. Apologies. X to the seventh times 2 plus x to the fourth to the 23rd. Okay. So similar idea at hand here. We're thinking, well, the only plausible choice for u is 2 plus x to the 4th. And if we take the derivative, our du dx is equal to 4x cubed dx. And we don't exactly have that, but we do have an x cubed in there. So what I would encourage you to do at this point is to rewrite the integral so we see the pieces we want to see. Oh, sorry, there shouldn't be a dx over here yet. Apologies. The one thing I would do here is rewrite this as 1/4 times du equal to x cubed times dx. So I'm looking for an x cubed times dx in my integral. So what I'm going to do is I'm going to rewrite this so that the x to the 7th is rewritten as x to the 4th times x to the 3rd. And I'm going to actually pull the x to the 3rd part to be next to the dx because I can. So I've got x to the 4th times 2 plus x to the 4th to the 23rd power times x cubed dx. And now we can start doing our u substitution. We can, some people call this like, we're changing, right? U substitution is the change of variables. We're changing all of our x's into u. Specifically, the differential dx has to turn into something with a du. So that x cubed times dx is going to equal our 1/4 times du. The thing we chose for u is obviously going to be u, but then there's some leftover x's. There's an x to the 4th left over. This is the part that's the back substitution. So for whatever's left over, we take our choice for u and we solve for x as much as necessary. So in this case, I'm just going to subtract 2 from both sides and say, okay, cool. U minus 2 is x to the 4th. There's no need to take the 4th root of both sides because I don't have just an x left over. I have an x to the 4th. So this x to the 4th exactly gets to be equal to u minus 2. So now we're going to translate all the way and say, you got the integral of u minus 2 times u times 1/4 du. And if we simplify, times u, what am I, it's u to the what? U to the 23rd. I would do 2 things next. I would pull out the constant multiple of 1/4 in front of the integral, and I'm going to distribute the u to the 23rd to the u minus 2 and get u to the 24th minus 2 times u to the 23rd. Now we're going to integrate each term. There is no reason to like break this up into 2 integrals. Like I know there was one of the problems he wrote solutions to where he broke it up into multiple integrals. It's really not a necessary step usually, but it's certainly not allowed. Just I don't see the point. So integrating or anti-differentiating these, we're going to get u to the 25th divided by 25 minus 2u to the 24th divided by 24 plus c. And then to end the problem, we're going to plug back in what x is equal to, what u is equal to, which is 2 plus x to the 4th. So we're going to rewrite this as 1/4 times 2 plus x to the 4th to the 25th divided by 25 minus 2 times 2 plus x to the 4th to the 24th divided by 24. And I'm not going to simplify the 2 over 24 to 1/12, even though I really want to. So there is a u substitution with a back substitution. I would say the most common examples of this are where you have some stuff stuck inside some function, and then the power of x outside is twice that power minus 1. Let's do another example. Yeah, let's see, where'd you go? Other example here. I don't love that one. Let's do, fine. Sure. This one's less exciting, but fine. Let's say we have a similar-ish thing. The integral of x cubed times the square root of x squared plus 9. And again, we only have one real, well, first of all, I should say, before we even start trying a u sub, we first just look at this, like, we can't just integrate it directly, right? I don't know what the antiderivative of that function is off the top of my head. So if I can't just simplify it or do it directly, then I start thinking about what sorts of options I have. And at this juncture, the only option we really have is U substitution. So we're going to try to pick a likely candidate for U. And there's only one real likely candidate here, the inside of the function. So we're going to choose U to equal x squared plus 9. I'm going to label things here. And then our differential du is just this derivative 2x multiplied by dx. I don't have a 2 in my integral, so I'm going to pull the 2 over to the other side and say 1/2 du is equal to x times dx. But I certainly do have an x times dx in my integral. It's just hiding in the x cubed. So I'm going to rewrite my integral. I mean, you can probably skip this step if you like to, but I think it's really helpful to rewrite the x cubed as x squared times x. And I like to put the x over next to the dx so I can really see, oh yeah, that's just going to be my 1/2 du. And my x dx is equal to 1/2 times du. The x squared plus 9 is just u. And the leftover x squared, well, we know that u is equal to x squared plus 9. So u minus 9 is equal to x squared. And that's our back substitution. We're going to fill in x squared with exactly u minus 9 in parentheses. So then we write it out. We get the integral of u minus 9 times the square root of u times 1/2 du, or better written, 1/2 times the integral of u minus 9 times u to the 1/2 power. We have to distribute here. You cannot integrate two parts multiplied together separately. You have to multiply it out first before you can start throwing antiderivatives at it. So we're going to multiply it out. We're going to have 1/2 times the antiderivative or integral of u to the first times u to the 1/2 is u to the 3/2, and 9 times u to the 1/2 is 9 times u to the 1/2. I can't pull the 9 out in front because it's not multiplied by everything. But I can pull the 1/2 out in front because the 1/2 is multiplied by everything. If you broke this up into two integrals, then you could pull out the 9. But again, I don't see that being particularly the way to go. So then we anti-differentiate. We add 1 to our powers. 3/2 plus 1 is 5/2. Dividing by 5/2 is multiplying by 2/5. Minus 9 times, we'll leave a space there. 1/2 plus 1 is 3/2. Multiplying by 3/2, sorry, dividing by 3/2 is multiplying by 2/3. Plus c, right? It's indefinite. We need to throw that c in there. And then we plug back in what u is equal to, again, because it's a definite integral. Sorry, because it's an indefinite integral, we have to end with the same variable we started with. Our answer is going to be a function, and the function is required to be using the same variable that our original integral started with. So we're going to get, I guess I could refrain from distributing the 1/2 here, although that seems silly to me, but okay. Our u was x squared plus 9, so we have 2/5 times x squared plus 9 to the 5/2 power. Minus, it seems dumb not to simplify that. That's just 6 times x squared plus 9 to the 3/2 power. Let's see. So those are two examples of u substitution with back substitution. When there's leftover x's, that's when you have to go back and look at what u is equal to and isolate x or some x to some power and then plug it back in. Okay. Yeah.
That's an integral, like if it had.
That's we're about to go there. Yeah. Good question. Yes. We're about to do some u sub for definite integral and see kind of the ways of doing that. Other questions about this? Sure. I'll come back to you. You're a good one. Where the integral go? Now I got lots of pages here. One moment. I have a specific example in mind, and it's not. There we go. Yeah, cool. So let's look at something relatively straightforward for our next example. And after we do a couple of these, we can talk about the practice exams or other exam kind of things. So let's say we want to find the integral from 0 to 2 of, we'll make it easy, 3x squared divided by 1 plus x cubed to the fourth power dx. Here I would argue there is a very, very obvious choice for u. It meets all the conditions we like it to meet. You all should write down what u is equal to and what du is equal to. I'll give you 30 seconds. Right. So in my opinion, the obvious choice for you is 1 plus x cubed. And my du is then the derivative of that multiplied by dx. And we're happy about this. All the pieces we want are showing up. So there's a few different ways people go about this. I would encourage you to do it the following way. The way I'm about to show you to do it is, I think, the best way of doing a definite integral with a u sub, but it's not the only way. So here's what I would recommend doing. We're going to rewrite this integral as being equal to, I'm going to leave off the limits for a moment. I'm just going to replace my 3x squared dx with du. You can put a du here, or you can put a 1 times du, whichever way you prefer. I prefer the 1. And the denominator, I have a u to the fourth. And then I think it's best to change the limits of integration. Bless you. So if x is equal to 0, u is going to equal 1 plus 0 cubed. And if x is equal to 2, u is equal to 1 plus 2 cubed, which is 9. So my new lower limit is 1. My new upper limit is 9. They might end up being out of order. Totally. So I'll point out that in our original integral, we're saying how much area is under the function f of x equal to 3x squared over 1 plus x cubed to the fourth between x equals 0 and x equals 2. And now we're doing a change of variables. And we're saying, oh, well, now we want to know how much area is under the function f of u equal to 1 over u to the fourth. But it's not between u equals 0 and u equals 2. It's between x equals 0 and x equals 2, which corresponds to, well, again, if x equals 0, I'm just plugging the 0 in for x right there, and u ends up being 1 plus 0 cubed. So if x equals 0, that corresponds to u equal to 1 in the lower limit. And similarly, if x equals 2, I get 1 plus 2 to the third is 1 plus 8, which is 9. That's my upper u limit. But I will point out, you have to pay attention to where the limits are. It could have been that I got a 9 on the bottom and a 1 on the top. They don't always end up being the smaller number in the bottom and the larger number in the top. We'll show you, I'll give you the next example. They'll end up switching. We'll see why. And then I would finish the problem without going back to x. Right? You shouldn't go back to your x. Okay. So if we antidifferentiate u to the negative fourth, we get u to the negative third divided by negative 3, evaluated from u equals 1 to u equals 9. And then we're just going to plug in. And we're going to get a not very nice answer, but 9 to the negative third divided by negative 3 minus 1 to the negative third divided by negative 3. Which sure is, I would leave it like that. I mean, okay, that's not true. I wouldn't leave it as 1 to the negative third. I'd probably rewrite it as negative 1 over 3 times 9 cubed plus 1/3. That feels slightly better, but whatever. Right, I brought the 9 down to the bottom, put the negative out in front, minus minus is plus, 1 to any power is 1. Again, that's a really good way to lose points on an exam, right? I didn't need to do that, but I couldn't help myself. So this is the way I would do it. Other people might not, although I think they're wrong. I think they're spending more time doing the problem than they really need to, is actually what I mean to say there. So another option here would be to say, well, I'm going to do my u sub. I'm going to get my du over u to the fourth, but I'm not going to think about changing the limits. I don't think you shouldn't write them. I think if you're going to not change them, you should still write them, but you should be explicit about the fact that those are x limits. So you can't plug them in for u. So then we anti-differentiate, we get u to the negative third divided by negative 3, evaluated from x equals 0 to x equals 2. And then we have to take the extra step, in my opinion, of changing back to x's. And this is going to be 1 plus x cubed to the negative third power divided by negative 3, evaluated from x equals 0 to x equals 2. And if we plug in 2, we get 1 plus 2 cubed to the negative third divided by negative 3 minus 1 plus 0 cubed to the negative third divided by negative 3, which ends up simplifying as 9 to the negative third over negative 3 minus 1 to any power is 1 over negative 3. The same answer, but we took more steps to get there. So you can kind of go either way, but if it were up to me, I would encourage you to do it this first way, to change your limits of integration and then just plug in those values. And when you change them, you do not go back to the original variable. We're just trying to get the area. It doesn't matter if we get there through u or through x. Our answer should be a number. It's a gross number, but it's a number. So questions or comments about that? We'll do another example, but it's fun. I'm sorry, I have them all. Oh, I know. I had, yeah. So let's say we have, sure, something like the following. The numbers might end up sucking. Oh, well. So we're going to have the integral of x squared times the square root of, sure, 9 minus x cubed, where x is going to go from 0 to 2 again. Sure, because I'm unoriginal. It's fine. So there's our integral. Question. Oh, thank you. Yes. Had it all ready to go, and then I totally forgot about it because the math started happening. Yes, appreciate it. Thank you very much. Also, if any of you attended the other day when I didn't hand out the sheet and you didn't respond to the message, like if you were there, let me know. Please do that so I can mark your attendance for that day. It's not a huge deal, but it does matter a little bit. All right, so same sort of idea here. We're going to do a U sub, and I think the obvious choice is, once again, the stuff that's inside a root or inside a function or in the denominator or in the exponent or whatever. So let's see here. Our du is going to be negative 3x squared dx. And we have an x squared times dx, so we have a negative 1/3 times du equal to x squared times dx. Since I know I'm going to do a u sub and I'm going to change my limits of integration, I might as well deal with the changing of them right now. So if x is equal to 0, u is going to equal 9 minus 0 cubed, which is just 9. And if x is equal to 2, u is going to equal 9 minus 2 cubed, which is 9 minus 8, which is 1. So when I rewrite this, and check this out, my lower limit, which was x equals 0, is now going to be u equal to 9. And my upper limit, which was x equal to 2, is now going to be u equal to 1. And yeah, they're out of order. Sometimes that happens. We'll live with it. And then my x squared dx gets replaced with a negative 1/3 times du. I'm going to put the negative 1/3 out in front and the du at the end. And then the rest of my integral is the square root of u. Yeah.
In that case, should we expect for the integral to be negative?
Not necessarily. No. In fact, I'm 100% sure it's not. Because if you look at the original function, x squared is always positive and the square root of something is always positive. So I actually am not expecting to get a negative answer. I'm expecting to get a positive answer. What that means, though, is this amount right here will probably end up being negative. Yeah. When you say the u part, what do you mean?
Like, since we did the u sub and now we're doing the integral from 9 to 1, and should we expect that one to be negative?
Not necessarily. It might be, but it might not be. But really, the thing is, I would say, is you don't need to worry about it. You can just do this problem like it doesn't matter. Like, it doesn't matter if it's 9 to 1 or not. I mean, it matters in that we have the correct order, but it doesn't matter that the bigger number is on the bottom and the higher number is on top. We can still just do the usual thing, meaning this is negative 1/3 times the integral from 9 to 1 of u to the 1/2. We anti-differentiate, we get negative 1/3 times u to the 3/2 times 2/3 from 9 to 1. That's going to be negative 2/9 times 1, you plug in 1 first, to the 3/2 minus 9 to the 3/2. Which I would simplify, because we can. That's going to be negative 2/9 times 1 to any power is 1. 9 to the 3/2 power is the square root of 9 cubed, which is 3 cubed, which is 27. So we end up getting negative 2/9 times negative 26, which is positive 52/9. One thing I will point out that a lot of people choose to do in a problem like this is when they get here, like, well, I could change the order if I want to. I could make this positive 1/3 times the integral from 1 to 9 of u to the 1/2. And that is totally valid as well and will result in the same answer. You'll end up getting 1/3 times 2/3 u to the 3/2 from 1 to 9. And surprise of surprises, you get 2/9 times 9 to the 3/2 minus 1 to the 3/2, which is still 2/9 times 26, which is still 52/9. So if you are uncomfortable with having them out of order, you can change it back to the regular order, but you have to change the sign, right? You have to slap on an additional negative sign. And if it's already negative, then that makes it positive. But you shouldn't let it perturb you. If the values are out of order, it's really, really not a problem. You can leave it there. Questions or comments or thoughts? Yes, that's an excellent question. A definite or indefinite? Sure, definite. Sure, let's have to think of one. Let's see here. Sure. Let me peruse my options here for a second before I don't want to come up with something too derivative. Oh, fine, we'll just make it. So let's say we have the integral of, yeah, x cubed times the, sure, 1 plus x to the 4th to the 5th power from 0 to 1. Yeah, try that. start writing things down. So obvious choice for you, my du is 4x cubed dx. 1/4 times du is equal to x cubed times dx. So there's my 1/4 du. All the things I just underlined, I'm going to not write them, and I'm going to write 1/4 du instead. Right? All of that is being replaced by my 1/4 du. And then that part right there, that's just my u, the fifth power. And then my new limits of integration. So if x equals 0, I get u equal to 1 plus 0. If x equals 1, I get u equal to 1 plus 1. So my new limit should be from 1 to 2. We can differentiate that. Be careful if you're me. Make sure your 4's and your u's look different. Then we're going to integrate. We get 1/4 times the antiderivative of u to the fifth is u to the sixth divided by 6 from 1 to 2. So that's going to be, sure, u to the sixth over 24. That was probably an unnecessary step there, whatever. So we're going to get 2 to the sixth over 24 minus 1 to the sixth over 24. I don't think you need to write 1 to any power. You know it's going to be 1. 2 to the sixth is 64, so we get 63 over 24. Yep. Yes, I'll try one. Oh, question. So if it's an indefinite interval, then we need a constant. So if you're doing a definite integral, meaning you're just finding the area under the curve or the net area under the curve above the x-axis, you never need a plus c. Or you could throw one in and then it would cancel, right? So if I put a plus c here, I would then plug in the 2 and get 2 to the 6 over 24 plus c minus 1 over 24 plus c, and then the c's would cancel out. Whereas if it's indefinite, if your answer is a function, then you have to have the plus c.
On the practice midterm, we
Mhm.
find the following as functions with a constant of integration. Is that the same?
Yes, that is the same thing. That means make sure there's a plus c at the end.
Okay.
In the most roundabout way. Yeah. It's so 2 raised to the 6th power is 2 times 2, 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. You're welcome. Got to play that 2048 game, right? All the powers of 2 right there. Yeah, it's good practice. Let's do one more, unless there's no questions about this. And then after that, we will turn our focus towards the exam you'll have tomorrow, or that most of you have tomorrow. Not all of you, but many of you. So try that one. The integral from 0 to the square root of pi of 4x times sine of x squared dx. You guys were ready for that. I was doing stuff while you were doing stuff. We should do something. Okay, let's take a look. So I think for most of the time at this juncture, the choice of u should feel like it's kind of obvious. It's usually something that's stuck inside another function. Here, definitely u is equal to x squared, or du is 2x dx. And normally I would isolate x here, but since I have a 4x there, it's really easy just to multiply both sides by 2 and say that 2 times du is equal to 4x times dx. Or you could have said du is 1/2 dx and then just before it. Either way is going to get to the same spot. So our 4x times dx is 2 du. So we're integrating sine of u times 2 du. And my new limits of integration, so if x equals 0, I get u equal to 0 squared. And if x equals the square root of pi, u is going to equal pi. I will also point out sometimes your limits of integration don't change because like your limits are 0 and 1 and your substitution is x squared and your new limits are 0 squared and 1 squared, which are also 0 and 1. Occasionally that will happen. I think there was 1 or 2 problems on the practice exam where that actually did happen. So just be aware that even if they don't look like they're changing, they're still changing. And so our new limits are from 0 to pi. We anti-differentiate 2 times sine of u and get negative 2 times cosine of u, evaluated from 0 to pi. So that's going to be negative 2 times cosine of pi minus negative 2 times cosine of 0. That's going to be negative 2 times negative 1 plus 2 times cosine of 0 is 1. So that's 2 plus 2, which is 4. So, how seriously should we take not simplifying? Could we have left our answer like this? I mean, technically, yes. I would still argue that you should there's probably an expectation that you should evaluate trig functions at known angles. But I would say if I was taking an exam and I felt like I was short on time, I would stop here and move on to other problems. And then if I have time at the end, go back and do the minimal amount of simplifying you think is required. Which I know is it's hard to know, right? You might ask him, what do you mean by don't simplify? Like, can I just stop here as soon as I've plugged in my limits of integration? I think technically yes. But again, you don't want to be arguing over a point where you misinterpreted the meaning of the instructions. So I might ask that question to my instructor. What does not simplifying all the way really mean? It's hard when it's integration. Okay, so I've got lots of other crazy looking integrals I could ask you about, but before I just start doing all kinds of wild things, are there questions about his practice midterm or my practice midterm? Yeah.
Do the approximation where the limit goes to infinity and you see like the rain and sun.
The one that was on my exam? The very last question? Sure. So, yeah. So this is the only question on my practice exam that maybe kind of differs wildly from his. He didn't ask one like this, but that doesn't mean we can't do it. So here is the question I asked. Find the area under f of x equal to 6x squared minus 2x plus 3 on the interval from 0 to 3 using the limit definition of the interval. Or limit definition of the area under a function. So our area under 6x squared minus 2x plus 3 from 0 to 3 is going to equal, and I would just throw this down before I did anything else. It's the limit, and then goes to infinity of the sum from k equals 1 to n of f of c sub k times delta x. Then we're going to fill in the necessary pieces. Starting with delta x. Delta x is just the width of each subinterval. It's your b minus a divided by n, which in this case, it's 3 minus 0 divided by n, which is just 3 over n. Your c sub k, if we're using right endpoints, is your a plus k times delta x, which in this case is 0 plus k times 3 over n, or just 3k over n. I don't think you need to write down the function since they already told it to you, but our function is 6x squared minus 2x plus 3. So when we plug in, when we find f of c sub k, it's going to be 6 times that squared minus 2 times that plus 3. So it's going to look kind of gross. Not surprising. These problems are always kind of gross. We're going to get the limit as n goes to infinity of the sum from k equals 1 to n of f of c sub k, which is going to be 6 times 3k over n squared minus 2 times 3k over n plus 3, all multiplied by my delta x, which is 3 over n. So then we do a couple things. I would simplify the entire inside here. Maybe in 2 steps, maybe in 1. So let's see. We have 6 times, this is going to be 9k squared over n. 6 times 9 is 54. I don't remember writing down the number before, but oh well. 54k squared over n squared. It does feel like something different than what I wrote down before. Oh well, it's just life. And then 2 times 3 is 6k over n. And then plus 3. All that times 3 over n. So then doing one more distribution here. The limit as n goes to infinity of the sum from k equals 1 to n. 3 times 54 is 162. K squared over n cubed minus 6 times 3 is 18. K over n squared plus 3 times 3 is 9 over n. And we're in the usual good spot of having every power of n be 1 larger than every corresponding power of k. That's always what you're hoping for when you do this kind of problem. Is n cubed k squared is good, n squared k to the first is good, n to the first k to the 0th is good. Break it apart into 3 pieces. 3 summations. The sum from k equals 1 to n. You're going to pull out the constant 162 over n cubed and leave the k squared behind. Same deal here. We're going to pull out the negative 18 over n squared and leave behind the sum from k equals 1 to n of k. Plus, we're going to pull out the 9 over n and leave behind the sum from k equals 1 to n of 1. And here's something you definitely should probably write down on your page of notes is the formulas for the sum of from k equals 1 to n of k, sum from k equals 1 to n of k squared, maybe even k cubed. So here's what we get. Limit as n goes to infinity of 162 over n cubed times the formula for the sum from k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 divided by 6 minus 18 over n squared times the formula for the sum from k equals 1 to n of k is n times n plus 1 divided by 2. And finally, 9 over n times the sum of 1 n times is just n. And then we're going to go straight to the answer. This expression, the leading term on top would be 162 times 2n cubed. And the leading term on the bottom would be 6n cubed. So the quotient of the leading coefficients is 162 times 2 over 6 minus 18 over 2 plus 9. Those cancel, so we're left with whatever 162 divided by 3 is, which is what? 54. Which I hope is right. Question. You've done all this work. Should you check your answer? I think no. Because you've done all the work mostly right. Maybe all the way right. But if you check your answer, you get a different number, then you're going to spend time trying to fix this mistake and trying to figure out where did I make an error. It's probably not the best use of your time if you've already done most of this question most of the way right. Yeah. Sure. So I didn't draw the picture that I usually draw, but if you think about like the fact that you're trying to integrate, you're trying to break up the interval from 0 to 3 into n subintervals. So here's my c sub 1, my c sub 2, my c sub 3, all the way to my last one here being c sub n. Well, my C sub 1 is just 0 plus delta x. My C sub 2 is 0 plus 2 delta x's. My C sub 3 is 0 plus 3 delta x's. So it seems not like a far reach to say that, oh, well, if C sub 3 is 0 plus 3 times delta x, then C sub k is going to be 0 plus k times delta x. We're just adding delta x k times. Our delta x was 3 over n, so we end up getting 3k over n.
Thank you.
You have a question? No? Okay, sure. Oh, yeah. I feel like there's something else I want to say here. No, I guess not. But I would say I don't really draw this picture for that because we kind of just it would be good to remember instead of working it out in an exam that you can just find C sub k by taking your A value, which is your lower limit value, plus k times whatever your delta x is. All right.
Thank you.
On mine or his? I mean, they're probably similar, but they're very similar. Yes. Totally. Yeah. So let me just make something up. Sure. Here, let me just, you can just. So 5B. Yeah, let's see here. So got to think for a minute here. No, what's that? Oh, 5E. Okay, okay, go. I was about to come up with something very different. Sure. Yeah. So sure, let's start making stuff up. So I'm going to give you the information first, and then we'll ask for what we're going to find. So we're given the following two things. That sure, the average value of f of x over the interval from 1 to 7 is 5. And the integral from, how terrible do I want this to be? Not that terrible. From 1 to 4 of 3 times your function plus, let me think for a second here. This one, sure, that's going to be fine. Plus x squared dx is equal to 20. Find the integral from 4 to 7 of f of x dx. And so the idea here is we're going to be using two pieces of information, really. We're going to be using the fact that we know that the integral from 1 to 4 of f of x dx plus the integral from 4 to 7 of f of x dx is equal to the integral from 1 to 7 of x dx. We're going to be using that, and then we're going to try to fill in all the pieces. So we're trying to find this part here. Meaning we need the other two pieces to be able to figure it out. Let me zoom in a little bit here. So part 1 tells us the average value of the function over the interval is 5. What that means for us from part 1 is that 1 over 7 minus 1 times the integral from 1 to 7 of f of x is equal to 5. Or phrased another way, multiplying both sides by 6, the integral from 1 to 7 of f of x dx is equal to 5 times 6, or 30. So this part here is equal to 30. This part here, we're going to break it up. So part 2, I'm going to rewrite this as 3 times the integral from 1 to 4 of f of x dx plus the integral from 1 to 4 of x squared dx is equal to 20. So I'm going to find this part here, right? I can anti-differentiate that. So I'm going to get that 3 times the integral from 1 to 4 of f of x dx plus, let's figure out what this is right here. So the integral from 1 to 4 of x squared dx is equal to x cubed over 3, evaluated from 1 to 4. 4 cubed is 64 divided by 3, minus 1 cubed is 1 divided by 3, which is 63 over 3, which is 21. So 3 times this integral plus 21 is equal to 20. So that means 3 times the integral from 1 to 4 of f of x is equal to -1, and the integral from 1 to 4 of f of x dx is equal to -1/3. Yeah.
Why did you multiply by 1%?
Because they told us the average value of f of x. So when we say the average value, it's the area under the curve divided by the length of the interval. That's what I'm doing right here. I'm dividing by the length of the interval from 1 to 7. Which is, I no, so this is the area divided by 6 or multiplied by 1/6. So then the integral from 1 to 4 of f of x dx is -1/3, kind of unexciting, but fine. And then to solve for the red part, I'm just going to add 1/3 to both sides. So we can say, I'm kind of out of room here, but okay, that the integral from 4 to 7 of f of x dx, what we were asked to find, is equal to the integral from 1 to 7 minus the integral from 1 to 4, which is equal to 30 minus -1/3, which is 30 plus 1/3. Or if you like improper fractions, it's 91/3. Other questions? Sure, but I don't think it's a good use of your time. So if you saw this exact question on the actual exam, I wouldn't do it. It took me a long time to do it. That said, I will briefly talk about how you would do it. So his extra credit problem is the following. What I'd really like to do is actually show you a different problem that I think is more plausible to be asked, but we can do this one. So it says, show that the approximation in problem 2b, which is the average of R4, L4, and M2. So we're going to show that, actually, so I think I'm going to say no, because there is a video of me doing this problem already. So you can watch the video, but I'm going to answer your question with a different question that I think is a plausible exam question that is in a similar vein. So here's what I think you could ask. Show that if f of x is a degree 1 polynomial on an interval from, let's say, 0 to 10, then the midpoint approximation using, let's say, approximation, sure I can spell, using 5 subintervals. 5, yeah, sure, I'll be kind. Is exactly the integral from 0 to 10 of f of x dx. Oh, sorry, yeah. Sorry, I forgot I zoomed in so much. Apologies. You should let me know right away. You can say, hey, James, we can't see. So again, show that if f of x is a degree 1 polynomial on really any interval, but specifically from 0 to 10, then the midpoint approximation using 5 subintervals is exactly the integral from 0 to 10 of f of x, which I'm pretty sure is true. So here's how you would approach a problem like this. You're just going to calculate the thing both ways. What's our function? Well, we don't know exactly, right? It's linear, right? It's a degree one polynomial. So just like in the other problem where the function you have to write has to be very general, in the other extra credit problem, you would say that their function is like ax squared plus bx plus c. I'm gonna do the same sort of thing here. I'm gonna say that my function, f of x, is a times x plus b. And now I'm gonna write down my approximations. Yeah, approximations first. So first, the M5 approximation. So I'll point out that if I'm on an interval from 0 to 10, and I'm breaking it up into 5 subintervals, my delta x is obviously going to be how much? And my midpoints are going to be at 1 and 3 and 5 and 7 and 9, right? Because my endpoints were 2, 4, 6, 8, and 10. So here are my midpoints, here, 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 and here. So very, very broadly, the way we're going to calculate this is just saying it's going to be your delta x times f of each midpoint. So it's going to be f of 1 plus f of 3 plus f of 5 plus f of 7 plus f of 9, all times delta x, which is 2. So now we're going to calculate it. So our f of 1 is literally 1 times a plus b. Right? We just have to use the general polynomial that we have. In the other problem I did, when I plugged in f of 3, it was a times 3 squared plus b times 3 plus c. Don't worry, it's going to make sense when we finish it. So this is going to be f of 1, which is a plus b, plus f of 3, which is 3a plus b, plus f of 5, which is 5a plus b. I don't really need these parentheses, plus 7a plus b, plus 9a plus b, all times 2. Let's see, 1 plus 3 plus 5 plus 7 plus 9 is 25. So I get 25a plus what b plus b plus b plus b plus b is 5b, all times 2. That's going to be 50a plus 10b plus u. Now we're going to calculate it the other way by calculating the integral. So the integral from 0 to 10 of my function ax plus b, well, let's do it. So integrating this, we get a times x to the second over 2 plus b times x, evaluated from 0 to 10. If you plug in 10, you get a times 10 squared over 2 plus b times 10 minus a times 0 plus b times 0. And 10 squared over 2 is 50. I get 50a plus 10b, the same answer. So that shows that whether you use the midpoint approximation for a linear function or the integral for a linear function, the midpoint approximation exactly calculates the area. Kind of cool. Which again, if you think about a linear function, totally makes sense, right? If you have a line and you're finding the heights of the rectangles by using the midpoint of each section, you're essentially cutting off exactly as much as you're adding back on. I could actually draw it instead of just trying to show you what I mean, right? If you were, say, like, had a straight line like this, and we're breaking it up into, some number of subsections, well, then, like, if I use the midpoint here, look, the midpoint's exactly going to go right there, and I'm going to cut off as much area here that I'm going to add back on here. So it totally balances out. That's not true if it's non-linear, but it is true if it's linear. So kind of neat. Other questions? But for the other one, though, I do recommend going to watch the video. It's a pain in the butt, but it's the same process. It's just that the thing you're plugging it into is much grosser. Yeah. So what's it, the Earth thing? So yes, So that is actually, I made one up that was not a real thing on my practice exam, but the Earth thing, right? So the Earth thing. So here's what we've got. He's telling us to, so write a definite integral for the function Earth of x. Earth of x, and he just says the words, is the area under the curve 2 over root pi e to the negative t squared between, bless you, t equals 0 and t equals x. And I think all of you could write the definite integral that I just described. Do it. Right? That integral that represents the area under this curve between here and here. So to answer the, so someone on the chat asked a question about the previous thing we did. They asked why we use the function ax plus b for the function f of x, and it's because the problem specifically said show that if f of x is a degree 1 polynomial, which is just a times x to the first plus some constant b. Just like in the other question that Babson asked for problem 6, if you were doing that one, where'd you go? I lost my pages. Somewhere over here. I don't know. There we go. If you look at this question here for his extra credit question, which I know it's hard to see, but it says, show that if f of x is the degree 2 polynomial, then the approximation is the same as the integral. But you have to actually use a degree 2 polynomial, and it has to be general. You can't just pick one. So you have to say here, your function, your polynomial is ax squared plus bx plus c. In the same sort of way, for that one, we said, oh, our first degree polynomial has to be ax plus b. Or you could use then mx plus b. I just didn't want to use m because I was using m4 and I felt like it might have been confusing. So that's why I didn't use mx, I used ax. Okay, so back to this ERF question. So the area under the curve is the integral of the function 2 over root pi e to the negative t squared. My lower limit of integration is 0. My upper limit of integration is, and my thing I'm missing over here, dt. It better be t or you're going to lose a point. Like often that's not, well, no, it's always important, but it's especially important here. So then the second part of this question is to find the derivative of this function, ERF evaluated at, or say the function ERF of x squared evaluated at x equal to 2. And I would do this in maybe 2 or 3 parts. So first, I'm just going to write the function ERF, ERF of x squared is the integral from 0 to x squared of 2 over root pi e to the negative t squared dt. And then we're going to differentiate that. So the derivative of ERF of x squared, well, whenever you're differentiating an integral and the upper limit of integration or whatever the variable one is, if it's more complicated than just x, we know we have to multiply by the derivative of that input here. So we're going to input x squared to each t. You're going to get 2 over root pi times e to the negative x squared squared. And then we're going to multiply by what? 2x, the derivative of x squared. And then to finally answer the question, we're going to take all of that and then plug in 2 for every x. So this is going to end up equaling 2 over root pi times e to the negative 2 squared is 4 squared times 2 times 2. And technically, you should not do anything else. You shouldn't simplify this. But I mean, come on. If you simplified it, the 2 times 2 times 2 would be 8, and you would get 8 over root pi. And the e to the negative 4 squared is e to the what power? Positive or negative 16? Negative 16. right? That squaring is happening before the negative is happening there. Also, a good reason to not simplify, right? If you're already told not to simplify and you might be a little unsure what way something's going to go, save yourself the trouble, right? Don't. So again, really take those instructions to heart. If the instructions say to not simplify, and you definitely should read the instructions carefully, don't simplify. And I would say, I mean, I don't know if his test is actually going to look like this tomorrow. It might, but definitely for each question, please do yourself the favor of giving yourself the time to read the question slowly and carefully. That is the best thing you can do to help your success, I think. So that's how this Earth question goes. It's a little weird, but not that weird. It is a real function. This is the function that's like the right side of the z table in statistics. It's the area under the curve, under the normal curve. Yeah. Proofs. No, I really couldn't imagine. The only proof I could think of someone asking would be something related to the fundamental theorem of calculus, and I don't envision that happening. Again, I don't know Babson particularly well, so I can't speak to how similar or dissimilar his actual exam might be from this exam. But no, but that's all. That's that end of sentence there. I can't. I don't know. Other questions? You guys are all good? Ready? Well, if you're ready, then I might as well ask you a question. Sure. Let's do. Oh yeah, sure. This is terrible. Let's try this one. The integral from 0 to 1 of x to the 5th times the square root of 1 minus x cubed. Try that. Finish that one. I'm going to give you a couple more. Give you till 4:25, and then we'll go through all these problems. All right, let's take a look. So this first one is a u sub with a back sub, and it's definite. So our u is going to be 1 minus x cubed. Our du is going to be negative 3x squared dx. We're going to pull the negative 3 over to the other side, so negative 1/3 times du is equal to x squared times dx. Since we're going to change limits, since it's a u sub, we're also going to change limits of integration. This is where it gets a little tricky, I feel like. So if x is 0, u is 1, and if x is 1, u is 0. So when we rewrite this, we do need to switch the order of limits of integration. Actually, before I rewrite it though, I'm going to break it up as I want an x cubed times x squared times the square root of 1 minus x cubed dx. So my x squared dx, that's my negative 1/3 du. My 1 minus x cubed is my u. And then my x cubed, well, back sub, I have to take my u equal to 1 minus x cubed, add x cubed to the left, subtract u from the right. So x cubed is equal to 1 minus u. So that's what's going to be right there. All right, so rewriting this, there's a lot to keep track of here. We have the integral from 1 to 0. We have a 1 minus u. We have a square root of u. And we have a negative 1/3 times du. Fun times. So then I would do two things. I'd pull out the negative 1/3 front, but I'm actually going to change the sign and make it a positive 1/3 integral from 0 to 1. And I'm going to write the insides as 1 minus u times u to the 1/2 du. Distribute the 1/2, the u to the 1/2, and you get 1/3 times the integral from 0 to 1 of u to the 1/2 minus u to the 3/2. Anti-differentiate, you get u to the 3/2 times 2/3 minus u to the 5/2 times 2/5 from 0 to 1, which are kind of the best limits of integration ever, because when you plug in 1 to something to a power, you just get the coefficient. When you plug in 0, you get nothing. So you're going to get 1/3 times 2/3 minus 2/5 minus 0 minus 0. There's my answer. Let's not do any more with that. He asks a similar problem on his practice exam, right? It's like 5A or something. or 4A, I don't know where it is, whatever, whichever one it is. These next two problems are meant to be much, much different, easier, maybe. So we don't know how to anti-differentiate this function yet. And I do emphasize the yet, because we will learn how to anti-differentiate this. But for now, you don't need to, because the limits of integration are nice. If you remember that this function, y equal to the square root of something squared minus x squared, that's the top half of a circle. If you want more to see that, you can square both sides and then add x squared to the left and say, oh yeah, that's x squared plus y squared equals 25. That's a full circle of radius 5, but this is only the top half because if you write it like this, y has to be positive. So that's the top half of a circle with radius 5. So you're going from -5 to 5. And since we are going from -5 to 5, it's the entirety of that half circle. So that's going to end up equaling 1/2 times pi times your radius squared, which is 25 pi over 2. If the limits of integration were 0 to 5, that'd be a quarter of the circle, and we get 25 pi over 4. Or if it was -5 to 0, we'd also get a quarter of a circle. So make sure you pay attention to what the limits of integration are if you've got one of these half circle things. Similar idea for this last one in that we're just going to draw it. So if we draw the opposite value of 2x minus 7, when x is 7/2 or 3.5, that's when we're going to hit the bottom. I don't really care. I don't care about being specific here. Sure, there's 1, there's 9, there's 7 over 2. So it's going to do something like this. Oh, look, I've got triangles. I know how to find the area of a triangle. 1/2 base times height. So this first triangle, well, the first triangle has a base of 7/2 minus 1, which is 5/2, and a height of, if you plug in 1 to your function, which is the absolute value of 2x minus 7, 2 minus 7 is -5, and the absolute value is +5. So I get 1/2 my base times my height. And then my second triangle has a base of 9 minus 7/2, which is 18/2 minus 7/2, which is 11/2. And there's a 1/2 in front of that, times my height. And if you plug in 9, 18 minus 7 is 11. So I end up getting 25 over 4 plus 121 over 4, which is 146 over 4. So if you do have an absolute value in a definite integral, you should draw it and just find the areas of those triangles. That is the best way to do it by far. As long as it's an absolute value of a linear function. If it's nonlinear, then, well, you probably shouldn't be seeing that yet. All right, it's 4:30. I've said all I can say. Good luck on your exam tomorrow. Do check out the practice exams that I posted on Canvas, as well as the one that he posted. And make sure you're ready. Make sure you sleep. Make sure you read the questions carefully and slowly. I can't say it enough times.